Okay, so guys, thank you so much for coming. It's good to see all of you. I hope that you've had a good weekend and maybe a chance to even start studying for our exam a little bit. What my plan is for this review is I'm going to spend maybe 5 or 10 minutes just on an overview of everything in terms of like how to organize yourself as you're getting ready for Thursday's test. And then most of the time in the next 2 hours, I'm going to work through as many of these 10 problems in this review session problems page. This is in Canvas. So I will write all the questions down, but if you want, you can also just watch the session and not take a huge notes if you'd rather just kind of listen and focus, because I do have all this stuff typed up in Canvas already for you. Okay, so as far as the midterm goes, you guys already kind of know. I'm just going to again give a brief overview for our second exam, which is on Thursday. You'll have the whole class to do the exam, and quite possibly I'll let you take something home. I haven't outwritten the test yet, so I don't know exactly how I'm going to do it, but more likely than not, the way I tend to end up is too many great questions to ask, and so I have to let people have a little more time. So I might do that again, just like I did with the first exam. Don't be surprised. But anyway, the exam covers chapter 7. So this is about recurrence relations. And there's a couple of main things about recurrence relations that you're going to want to be able to deal with. One is you're going to want to practice how to set them up. Okay, so if it's a real physical problem, if it's like an actual problem, like dealing with chessboards or, making arrangements of objects or whatever, you might have to actually set up an example of a recurrence relation and then solving them. And we certainly did not learn how to solve every recurrence relation that could ever exist. We talked mostly about linear recurrence relations that are either homogeneous or non-homogeneous, and I'm going to go over that again today, but they have to be kind of linear in their form and in their structure in order for us to actually know how to solve these, okay? So obviously, I'm not going to ask you to solve some recurrence relation that's not of a nice type that we've seen before. You should expect to see something familiar there. And then also in chapter 7, there was a brief conversation about generating functions. So you should be thinking a little bit about that as well. Again, what is a generating function? How can you create a physical problem that has a certain generating function? Or how can you use a generating function to solve a combinatorics problem? So there's some examples of that as well. We're going to look at some in this review packet as well. So that's kind of chapter 7. And then we jumped ahead to chapter 11. And this is just basic graph theory. And so there's a lot of terminology in the graph theory portion. Certainly some of the main highlights were things like isomorphisms. So knowing if graphs are isomorphic or not. Then we talked a lot about walks versus paths versus trails, and then cycles, all of these kinds of things. And of course, within that, we have things like Hamilton cycles, Hamilton paths, Eulerian trails. They could be open, they could be closed. Whether those things exist, there were certainly some questions on the quiz recently that were related to those ideas for sure. So you have topics along those lines. And then we also talked about bipartite graphs. And then we talked about trees a little bit as well. So being familiar with all of that would be a really good idea. And then there's certain special types of graphs. So you have, cycle graphs, C sub n, the complete graph, K sub n, the complete bipartite graph, which is KMN, and so on, that you want to be familiar with. We've done quite a bit of homework with these special types of graphs. So I could give you any graph really and ask you a bunch of questions. Does it have open or closed Eulerian trails? Does it have a Hamilton cycle? Is it bipartite? Is it a tree? Another one, well, actually, I'm going to put this with chapter 12, the issue of the planar graphs, but planar graphs. So we've talked a little bit more about that recently, but you could also put that in the basic graph theory section if you wanted to. So stuff like that. Planar graphs, of course, we have things like edge analysis that I did in that extra video that you guys took notes on. So if a graph is planar, then you can say something about a bound on how many edges it would have. There's the Euler's formula. So this is an important one. The number of regions minus the number of edges plus the number of vertices adds up to the number of connected components plus 1. So I can add a plus 1 on the end of that. And normally, if it is a connected graph, then the right-hand side is just equal to 2, which is the most common version of the formula that you would have ever seen. But anyway, so we use Euler's formula to sort of make this edge analysis work. I should have mentioned, I forgot over here in the basic graph theory to mention the handshaking theorem. Let me come back and add that here. That's a big one. We use that a lot, right? If you add up the degrees of the vertices in a graph, it should add up to 2 times the number of edges.
What about spanning trees?
Oh, spanning trees, that would be, yeah, for sure. As an example of inside of trees, we have spanning trees. So that's well worth knowing what that means as well, for sure. There's also kind of a handshaking theorem type of thing for planar graphs as well, which is you can talk about the degrees of the regions. And again, if you add up the degrees of all the regions of a planar graph, it adds up to twice the number of edges. Remember, this only makes sense if the graph is planar, because you can't talk about regions unless you have a planar graph. Right. And then also along the lines, we generalize the idea of planar to crossing number. So Cn of a graph, the crossing number is just the fewest number of crossings that you can draw the graph with. So every bridge, every time you have 2 crossing edges in a graph, it costs you $1 million. So you try to make as few crossings as possible. So you get less highways crossing or less pipes crossing or whatever, just for the simplicity of your setup. So this is very quickly, in like 5 minutes, a quick overview of everything. Of course, in my review packet for the resources folder for this exam, I go into a bit more detail about it, including a list of what kind of things should you be able to do with this stuff. So take a look at that as well, but I just wanted to kind of get this into your head. In terms of the exam breakdown, I would expect chapter 7 might be around 35 to 40% of the exam. And I would expect chapter 11 to be kind of similar, maybe 35 to 40%. And then chapter 12 has been a little bit brief, more of a brief discussion so far. So whatever we need the rest of this to be, what, 20 to 30? But if my math is supposed to add up to 100%. Something like that. So maybe slightly less emphasis on this, but not enough that you would want to like just ignore it, right? All 3 parts. You could almost think of it as a third, a third, a third for everything here in terms of the breakdown of the exam. The other thing I'm going to recommend, guys, is that you maybe think about bringing some colored pens or markers or just something to write with. Obviously, you can bring stuff. But like if you're trying to trace out like an Eulerian trail or something and you want to like draw on the graphs, it's not a bad idea to have some colors with you on Thursday for the exam, just so you can make it easier for yourself to see it. It's just a suggestion. If you need some pens or markers, go up to the math department office and beg them for some colored pens. They have plenty up there, and just tell them you're taking Dr. Annan's combinatorics class and you have a test and you need to have some colors. I'm sure they could give some to you. Does anybody have any questions about the overview? This is just like broad, sort of from, up in an airplane view of everything before we kind of get into the details of it by looking at some examples. And I do have so I guess I can't see my Zoom chat, but you guys hopefully can all hear me out there. Okay. All right, so I'm going to go ahead and continue here. I'm going to erase this, and we're going to spend the rest of this hour and 45 minutes doing some actual problems. And I'm going to do as many of these as I can tonight. Anything I don't get done tonight, I will start with on Wednesday's review, and I will send out video of both of these review sessions just so we have it all. But I'm just going to start right from the beginning here. So let's do some practice problems. Any of these practice problems that we're going to do would make good test questions. So I'm just giving you like a chance to get a little bit of practice on the fly with this, and we'll talk it through kind of together. So the first one is, let's let H sub n denote the number of ways. H sub n is the number of ways to tile a 2 by n chessboard. Okay, so we're going to take a 2 by n chessboard using 1 by 2 horizontal tiles. And then we also have 2 by 1 vertical tiles. Hi. And 2 by 2 square tiles. So you guys just missed the overview. I'm recording this, so you can go back and watch the first 10 minutes of it later. It's just kind of like, what are all the topics and how much percent for each part of the exam kind of thing. Yeah, glad you could make it. I hope it wasn't pouring too bad out there.
Oh, no, we just had them on.
Oh, you did? Oh, okay, I see. Yeah. Okay. Yeah, some people came in and said it was pouring rain, and I was like, well, no wonder there's not that many people here. Actually, this is not a bad turnout. I have 5 people in the room, and I have another 4 people on the Zoom, so that's pretty good. Okay, so this would be a typical Dr. Annan thing to do. Every other problem that you've seen, it's always been a 1 by n board. So here I've decided to like amp it up to a 2 by n board. And what we're going to do on this problem is find an explicit formula for H sub n. There's definitely going to be something like this on the exam, where I'm going to ask you to set up a recurrence relation. Now, this problem is asking us to set up the relation for H sub n and to explicitly solve it. So, of course, sometimes you might get a problem where you're already given the recurrence relation and you just have to solve it. Other times I might just ask you to set one up. But this one's actually the whole ball of wax. Is it clear that it's a recurrence relation problem, though? So it looks kind of like those sorts of problems, right? Where we have, obviously, our number of ways of doing this is indexed by n, right? In H sub n, we're talking about a chessboard that sounds exactly like a recurrence relation. So let me just suggest that drawing a little visual picture of this might not be a bad idea. So you're going to have sort of 2 by n sort of means you have something like this, right? So 2 rows, and then, so this is like, two rows, and then you have n columns here. Okay. And so in order to figure this out, does anybody have a suggestion? And again, if you're out there in Zoom, you can certainly offer suggestions as well. You just have to unmute your microphone and just shout out for the group here. We've also got people in the room. Does anybody have a suggestion for how to approach this? Jose?
So since we don't have any restrictions,
Right.
we, look at the cases where we start. We have 3 ways to start this.
Okay, and I like thinking of it for how many ways there are to, or looking at the different ways to start the tiling. Some people, and I noticed this on the homework when I read it, they work on the back side of it and they say, well, here's what we could finish with. It really doesn't matter, but for me, I just like going left to right. Mm-hmm. So I would probably do that. So can somebody, that marker isn't too good. Can somebody suggest a good case that we could like, what would be like one case that we would have for how we're starting off our tiling? Jose said there's 3 cases. Can somebody tell me what one of the cases would be?
Horizontal tiles.
Sorry?
The horizontal tiles.
Okay, the horizontal tiles. So start with horizontal tiles. Now, so the horizontal tiles are 1 by 2. So I could start with like a horizontal tile here. I'm going to shade this in blue. Now, actually, you know, it might even be better if let me just redraw it over here, because I'm going to want to have this picture several times in my solution. So I'm just going to kind of draw it like this. So I could start with a 1 by 2 tile here. Now, guys, in this case, I don't have any 1 by 1 tiles. Okay, now that would be another problem you could do. You could say, well, what if we also have 1 by 1 tiles? But if I don't have 1 by 1 tiles and I use a horizontal tile in that first row, then do you agree that I have to also use another 1 by 2 tile in the second row right below it? It's the only thing you can do, right? You have to then use the tile that's horizontal here as well. Okay? And that would be one way to start. And then the question would be, how many ways are there to finish tiling this board? Now it's a smaller board, right? The remaining board is 2 by what? N minus 2? So how many ways are there to finish tiling it?
H of n minus 2.
H n minus 2, exactly. So we have H of n minus 2 ways to finish tiling this board. And guys, don't go overboard on these explanations. It's very easy to sink a lot of time into like saying, oh, I'm going to write 3 paragraphs about that. Don't need to. Just give me a brief half of a line, or basically a fragment of a sentence is all you have to write down. Go fast. Go fast on this. You don't need to like, if it seems, sometimes people think, oh, it's too easy, it can't be that fast. Well, sometimes it is. Just go ahead and write it down. Okay, what's another case?
Vertical tiles.
Start with the vertical tiles. Okay, great. So we could start with vertical tiles. So again, I'm going to just draw a little bit of a snapshot of my little 2 by N chessboard here. But this time I'm going to fill in vertical tiles. So here's a vertical tile right here. Now, after I do that vertical tile, do I need to put another vertical tile next to it? Not necessarily, because I now have a choice to finish this. So what is this now? This is a 2 by N minus 1 board. And I can now start over and use anything I want. I could use 2 horizontal tiles, I could use 2 more vertical tiles, or I could use 1 more vertical tile actually, or I could use the square tile, the 2 by 2. So at this point, how many ways are there to finish this?
Hn minus 1.
Exactly. Hn minus 1. And guys, you can also take advantage of this trick. Ditto symbols, you'll save some time. Right? Every little second that you can save is a good one to do. Okay, and then for the third case, what's the last option? Jose mentioned there are 3 cases. I've got 2 of them up there so far.
Square tiles.
Yep, we also have the 2 by 2 square tiles. So let's draw a picture of that. So start with square tile. Okay, so again, I'm going to draw my little picture here, just to have a visual of it. Actually, so some people might wonder, well, do you have to draw these pictures? And really you don't. Like if you just explained, you could start with a horizontal tile and then there would be HN minus 2 ways to finish. That would be fine. I just think the pictures are kind of helpful if I'm not quite sure what I'm doing yet, so I can see all of the cases. How many ways are there to finish this last one?
HN minus 2.
Exactly, HN minus 2 ways to finish tiling that. Okay, so I always like to pause and ask myself, make sure there's no overlap of the cases. There's no way that you could have two identical tilings that would be listed in more than one of these three places, right? So obviously they're all starting differently. So you're not gonna have something that could be here and here, for example, right? Nothing could be here and here. They're all totally different. So there's no overlap of the cases. That's one thing to double check. The second thing is every case is covered, right? You've looked at every kind of tile that you have, and you've started with each of those. So every tiling possible is going to land in exactly one of these cases. That's the point I'm trying to make. You just have to make sure there's nothing like left over. Okay, there's no gaps. There's no tiling that somehow doesn't get listed in any case, or there's no tiling that could be in two of these cases. So that's important. But once I've done that, then can we write down the recurrence relation? Okay, so what is it going to be?
The addition principle.
By the addition principle, okay? What do we have?
HN minus 1.
Oops, sorry. HN minus 1, okay?
Plus 2 HN minus 2.
Okay, guys, take a look, right? If we just add up these cases, HN minus 2 plus HN minus 1 plus HN minus 2, it gives us this right here. Sort of lost my subscript there. That's the formula. Okay, now in addition to this, we should also write down some base cases, because that's part of the recurrence relation. On the quiz last week, some people got a little bit in trouble because they started by telling me what H0 is. Now, on a physical chessboard, which would be a 1x0 board, that actually doesn't really exist. It doesn't make sense. So guys, on these physical problems, where it's actually so I could just give you this recurrence relation, and if I did that, there would be nothing wrong with giving you these two base cases. But if it's a physical problem, then you actually should start with something that physically makes sense. So a 1x1 board would definitely make sense. Or a two, in this case it would be a 2x1 board would make sense. So what is H sub 1? If I have a 2x1 chessboard here, how many ways are there to tile this 2x1 board if these are the kind of tiles that I have? One way, right? Which is to use the vertical tile. So H1 would equal 1. Okay. And then what about, and by the way, I'm doing two initial conditions because this is a second order recurrence relation. Right? So for a second order relation, you would need, one way I like to think about this is if I actually wanted to figure out what H3 is, I would have to know H2 and H1. So that's why I'm starting off by writing them both down. If my board was a 2x2 board, how many ways would there be to tile the 2x2 board?
2.
How many?
3.
3. Yeah, there's going to be 3, right? Because I can do what? I could fill the whole thing with my 2x2 square, or I could do 2 horizontal tiles on top of each other, or I could do 2 vertical tiles right next to each other. So this one should be equal to 3, right? And I liked it on the quiz. It was kind of nice. People were like showing me how they got their base cases. So you could draw the vertical tile here. You could draw the full square. And you could draw like 2 vertical tiles like that. And then you could draw 2 horizontal tiles like that. You don't technically have to do that, but it was kind of helpful to see. I think it helped people get the right answers for the initial values. But again, the biggest mistake was people tried on the quiz, people tried to write down h of 0. And there was no such thing as a zero dimensional thing. And so people were just kind of guessing that it was equal to either 0 or 1, and depending on what you guessed, you could end up with the wrong thing. And so some people ended up getting the wrong answer for part B because they had the wrong initial values. So anyway, just be a little careful with that. Otherwise, nothing too hard about it. Now, in this case, we actually need to go from here and solve this relation. Are there any questions so far? Probably. So if this was on the exam and you got this wrong, but then we go to part B where you're solving it and you use the right technique, of course you're going to get the wrong answer for part B also. But if you get the right technique going, I'm going to give you as much partial credit as I can, possibly all of the credit if you can actually solve it. The trouble is sometimes when you get the relation wrong, then like for example, the characteristic equation becomes like impossible to factor or something like that. So it's not always easy to then do part B, but at least if you make the effort with it, I'll give whatever credit I'm possibly able to. So try to stick with it, even if you're feeling a little bit unconfident. But to solve this, can somebody remind me what is our technique for solving this? Is this homogeneous or not homogeneous?
Homogeneous.
Yeah.
Yes, somebody in the chat. Yes, it is homogeneous. So that is true because there's no term on the right-hand side that is not attached to some h of n minus k. So this is definitely second order. It's also homogeneous. I'll just add that here. So because it's homogeneous, we don't have to do the whole thing where we have a three-step process. We can just go straight into this. Does anybody remember what the technique is?
Guess Q to Q.
Awesome. We make a guess of h sub n equals q to the n. Exactly. And the idea here is we have to figure out what q is. And to get that, we're going to just plug this into our recurrence relation. So then q to the n is equal to q to the n minus 1 plus 2 times q to the n minus 2. Okay. And then we just do algebra on this as best we can. In this case, we can cancel as many q's as possible. I have n minus 2 powers of q here. So if I cancel as many of them as possible, I'll get q squared equals q plus 2. All right. And here you really do have to kind of depend on, I'm not going to be trying to create something that you can't deal with in terms of factoring it. Otherwise, you can't really do the problem. So it should be a quadratic is always factorable. So if it's a second order recurrence relation, no matter what, you should be able to get the roots for that. Even if they're imaginary or maybe not nice numbers, you should be able to get it. In this case, we don't even really need the quadratic formula because this actually factors super nice, right? So we can kind of just look at this one and we see that it factors as q minus 2 times q plus 1. And so my roots here are 2 or negative 1. And the idea now is that we can create two different solutions here, 2 to the n or negative 1 to the n. And the final general solution, as I like to call it, is just a generic linear combination of these two solutions. So h sub n equals c1 times 2 to the n plus c2 times negative 1 to the n. This would be the general solution to the recurrence relation. And is this going to end up being my final answer? Not yet, because what do I still have to figure out? The C1 and the C2, the constants, right? And we can figure those out by using the initial values, exactly. So I'm going to use the initial values. So for example, I already know that H1 is equal to 1. That was our initial value earlier. And if I actually plug in n equals 1, then I see that I get, so I'm just putting 1 in for n on both sides of the equal sign here. So I'm just going to get 2 times C1 and then a minus on C2. And then similarly, if I plug in n equals 2, I'm supposed to get 3 for the answer. But if I plug it in and just see what comes out, I'm going to get 4c1 plus c2. Okay? So you get this little set of two equations and two unknowns. If we were doing linear algebra right now, we'd put it in a matrix and do a whole solution to it formally, but I think on this one, I don't mind if you just kind of wing it. You can see that if you add the two equations together, you can make the C2 disappear, right? So if you add the two together, you'll get 4 on the left side, and on the right side, you'll get 6C1. I'm totally okay with that. Guys, it is not going to be my goal to like test you on stuff that's outside of this class. So I'm probably not going to make this part of the problem some disaster calculation, right? It's not going to be really what I'm looking for. So in this case, C1 is 2/3. Once I know what C1 is, I should be able to solve for C2 pretty easily. You guys can confirm this with me. I think it's 1/3. Right? Yeah, I think that looks good.
Yeah.
So C2 is 1/3. And so my final answer would be 2/3 times the quantity 2 to the n plus 1/3 times the quantity -1 to the n. Now, one thing that I would recommend doing if you have a little extra time is you might just say, well, you know, I didn't really need to figure out H3, but I'm just curious what it is. So you could just do something like this. You could say, here's my 2x3 chessboard. How many ways could I have tiled this? And just directly figure it out. So I could do a square and then a vertical tile. I'll use S and V and H for this. So I could do a square tile and then a vertical tile, or I could do a vertical tile and then a square tile. Or I could do 2 horizontals above each other and then a vertical tile. Or I could do, so that's that way. Or I could do 3 vertical tiles, right? Or I could do a vertical tile first and then 2 horizontal tiles above each other, above and below each other. And I think that's everything you could do. 1, 2, 3, 4 ways to do it. And the reason I'm suggesting this is just to check your answer here. Like if I plug in n equals 3 over here into my final answer, I'm going to get 2 cubed is 8. So times 2/3, that's 16/3 minus 1/3, which is 15/3, which is 5. So that suggests that, did I forget something over here?
Oh, it's the SD.
Oh, I'm sorry, these are 2 different ones. Yeah, 1, 2, 3, 4, 5. Yeah, there's 5. I said 4. There's 5 of them here. So I listed 5 ways I could do the picture. The formula confirms that. It's going to be very unlikely that your answer is wrong if you've tested it against like the next value and it's still working. So I feel pretty confident in that answer. Questions? Anybody have any issues with that one? Seems okay. Okay, let's try another one then. So obviously you can tell I like these tiling examples. The other thing I could do, instead of asking you to fully solve for h sub n, I could do what I did on the quiz, which is set up the recurrence relation and then figure out like h10 or something like that. So you'd start with like h1, h2, h3, h4, h5, and build your way up using this relation. There were some people on the quiz, I think I asked for like h sub 9, and people were like breaking it down. They did like h8 plus h5, and then they took this one and wrote it as h7 plus h4, and then h5 turned into h4 plus h1 or something. This is on the one on the quiz, and this became a mess. So some people still did get it to work out, but it's less likely to work out than if you just work up. So just figure out, okay, what is H1? What is H2? What is H3? What is H4? What is H5? Go up in order rather than trying to break something big down like this, because this just gets, is you have to start combining the terms, and It's just kind of difficult to do that. It's not difficult, it's just messy, I should say. It's just messy to do that. So anyway, so that is that example. Guys, I'm doing a little study session here. So if you're quiet, you can hang out in here, but I am going to be busy in here until about 7. Yeah.
I'll just.
That's fine. That's totally fine. Okay, let's go on to another problem. This next one is an interesting one. So number 2, a coding system. A coding system encodes messages using digits 0, 1, 2, 3, 4, 5, 6, and 7. Okay. A message is valid. I'm going to define the word here, valid. A message is valid only when there are an even number of 7s. And then the question is, how many valid messages of length n are there? Let you guys write that down while I erase the rest of the board here. How many valid messages of length n are there? So it's a counting problem because I'm saying how many. And always good to try to place the material. I have to make sure, is this really about recurrence relations? I mean, the only other thing on this exam is graph theory. I don't see a lot of pictures here. So it seems most likely that this has to do with, setting up the number of valid messages of length n in terms of shorter messages of length n minus 1. So, pardon?
This is a graph.
Well, that's my question. I said the only other thing besides recurrence relations that's on this exam is graph theory. And so I said, does this look like a graph theory problem? It doesn't really look like it to me. This looks like I have n slots. And I'm just making strings of these digits. And a valid string would have, so something like this would be a valid string of length 6. As long as there's an even number of 7s, it's a valid string. So this one has 2 7s, so it would be valid, right? So that's kind of the idea. So this one would be valid, whereas, whoops, there's no 8. 2, 2. This is not valid because the second string I wrote down only has an odd number of 7s. There's just 1 7 there. So this is kind of the idea. So it's going to involve, so maybe we can do this. Let's let v sub n equal the number of valid strings of length n. Right, so more likely on the exam I would give you the notation for it, but anyway, so let's just use that notation. So if we had a shorter string, let's say of length n minus 1, that shorter string might already be valid, or it might not. But either way, I could make it valid by how I chose the last. See, all it takes is 1 digit to switch from an even to an odd number of 7s, right? So what we might do here is consider a string of length n minus 1, right? This is kind of the way that I would approach this. Now, guys, there is not necessarily only one recurrence relation for something. Not necessarily only one, but it's generally better if you can find the one of the lowest order possible. So you might be wondering, well, am I gonna need to look at strings of length n-2, n-3? Like how far back do I need to go? On that last problem we had, we ended up with something of order 2. And that made sense because we had tiles that were 2 by 2 that took up two spaces. But here, I actually claim we do not need to consider strings that are of shorter length than n-1. If I want to build a valid string of length n, I can take a string of length n-1, and depending on whether it's valid or not, that will then dictate how to put one more digit into the string so that it has length n, and you have to do it in such a way that you end up with something that is valid. Okay, but my point is, try not to create something that's unnecessarily large order. Yes.
If we start with 7, wouldn't that mean that there's a possibility after where we create like an odd situation, so we would need n-2?
So I claim that one of the cases would be starts with 7.
Right.
So you can have a string that starts with a 7, but if it starts with a 7, then here's my n-1 slots. And the key thing here is that what you need right now is an odd number of 7s in this part of the string, so that by the time you consider this extra one in the front, it becomes even. So, in other words, what we want to count right here, guys, is how many bad strings of length n-1 are there. So a bad string is one that would be not an even number of 7s. So I would want to put an odd number of 7s into these n-1 slots. Does anybody think they know how to count the bad strings of length n-1? Yeah, we could actually take the total number of strings of length n-1 and then subtract the ones that have an even number of 7s. If I want to know how many strings have an odd number of 7s of length n-1, I could take all strings of length n-1. What is the total number of strings of length n-1? These are my digits. So no constraints at all. If I want to make a string of length n-1 using those digits, how many strings could I make?
Be 8 to the n-1.
8, exactly, 8 to the n-1. I have 8 choices for the first slot, 8 choices for the second slot, 8 choices for the third slot. There's nothing about repeats or anything else being restricted, so we can make any string whatsoever. So total number of strings of length n-1 is going to be 8 to the n-1. Okay, and then the total number of strings of length n-1, I'm going to use my ditto trick again, feel free to use that, with an even number of 7s, because those are the ones now that we are trying to subtract right here. How many strings of length n-1 would have an even number of 7s? In other words, how many strings of length n-1 are valid? What's my notation for that?
V n-1.
V sub n-1, exactly. V sub n-1. And so these are actually the violations right now, if I want to think about it that way. And so what I end up with here is 8 to the n-1 minus V sub n-1. Those are the number of strings of length n-1 that have an odd number of sevens in them, and then by putting this 7 in the front, we make it a valid string. So there'll be this many valid strings in case 1. What do you suppose my second case is going to be? Does not start with a 7, exactly. The strings either start with a 7 or they don't. So does not or doesn't start with a 7. Obviously, you want to make sure that your two cases cover every scenario. Well, every string is either going to start with a 7 or it doesn't start with a 7. It's one way or the other. And then the question is, how many valid strings would we get in this case? So the first slot is here, and then the rest of the n-1 slots is here. So if it does not start with a 7, then how many things could it start with? Like, how many choices do I have for this?
7.
Yeah, it could be a 0, a 1, a 2, a 3, a 4, a 5, or a 6. There's 7 of those. So there's 7 choices for that first slot. Any one of the numbers except for a 7. And then assuming that that wasn't a 7, then you need to have an even number of 7s here. And what's the notation for that?
B n-1.
B n-1, exactly. So, and then by the multiplication principle, so we are using the stuff from earlier this semester a little bit here. By the multiplication principle, we get 7 times b sub n-1 valid strings in this case. Okay, and now I'm going to use the addition principle, right? So by the addition principle, v sub n should be 8 to the n-1 minus v sub n-1 plus 7 times v sub n-1. So I'm adding my two cases together. Everybody agrees, right, that there's no other cases? The string either starts with a 7 or it doesn't. These are non-overlapping cases, and every string is going to be either here or here. Right? That's the only possibilities. We might as well clean this up a little bit. This is actually 6 factors of Vn-1, and I'll put the 8 to the n-1 on the end of it. People following that all right?
Just a quick question.
Yeah, please.
So when we're doing the case 2 to 7.
Case 2, yeah.
The Vn-1 are the things that are not valid, right?
No, Vn-1, those are the valid strings. So those would be
Yeah.
strings, so you have an even number of 7s here. And then you're going to put a number in the front that's not a 7. So the total number of 7s will still be even by the time I'm done with that construction, because you had an even number of 7s, you added something in front that didn't have a 7 in it, so you still have an even number of 7s.
So the 2 Vn-1s are not the same. What I'm saying.
Right, well, this was going with, here it was a violation
Yeah.
to have an even number of 7s, because we wanted it to actually be odd so that we could add a 7 in front. I actually think that case 1 is the harder case. We just happened to do it first. But it would be easier probably to start with this case, say, oh, suppose that you don't start with a 7, when then all you have to do is take the number of valid strings and multiply by the number of digits you can put here. This case, I think, is the easier case. And then this is the other case. Yes.
For the case 1, the 8 to the part of n-1 is not clicking with the animal.
Okay, that's okay. So the string here is starting with a 7. So I'm not making any choices with that, by the way. This is not a number that we're multiplying for our choices. This is actually filling in that slot with a 7. The remaining n-1 slots, now that's where our ability to fill in the slots comes. And we need to have, in total, an odd number of 7s, but we're going to actually subtract violations. These are the violations here. What's the total number of ways of just making a license plate of length n-1 where I have all of these digits available? So I'm making any possible string that I want of length n-1. It's like a license plate problem. So I have, 8 possible digits for the first slot, meaning this slot. And then 8 choices for the second slot, 8 choices for the third slot, and I got n minus 1 of those slots, they each have 8 choices.
Okay.
Feel okay? Is everybody okay with that? So, yeah, again, I always think the harder part of these things is setting up the recurrence relation. The second part of this is we have to actually solve it now, because it does ask us how many valid messages are there. So we're gonna need to solve this. This one is a first order recurrence relation. Notice that we did not actually need to go down to v sub n minus 2 at all. Is this homogeneous or not homogeneous?
Not homogeneous.
Yeah, this is not homogeneous. This is not homogeneous because of this 8 to the n minus 1. So non-homogeneous. So if it's okay, guys, I'm going to erase the breakdown of the cases now so I can focus on solving this one. Okay, so let's do that. Let's come back over here. And when we have a non-homogeneous recurrence relation, we always solve it in sort of 3 steps. The first step is to actually just solve the corresponding homogeneous relation. Is that a hand?
Yeah.
Yeah,
Do you want
please.
to do initial conditions?
Oh, initial conditions. Yes, we should do initial conditions. Thank you. Yeah, sorry, before I go on, guys, let's do the initial conditions. Marcus is keeping me honest here. Valid strings of length 1. And I only need 1 base case because this is only a first order recurrence relation. So I just need to figure out how many valid strings would have length 1. So an even number of 7s. I have only 1 slot. How many ways can I fill in 1 slot so that I have an even number of 7s? Okay,
Zero.
just as a quick reference, the number 0 is even. So it does count. I don't think I've seen the correct answer yet. It's not 1. An even number of 7s. What would be an even number of 7s?
Oh, 7.
It would be 0 7s. So you as long as this string of length 1 is not a 7,
Oh,
Yeah.
it's good, right? So this could be a 0, it could be a 1, it could be a 2, it could be a 3, it could be a 4, it could be a 5, or it could be a 6. There's actually 7 of them. I think that's the initial value. Yeah. So as long as you don't put the 7 in that slot, you have an even number of 7s. You have no 7s. Well, that's even. Yeah, yeah. Sometimes people get tripped up by that. They're like, is 0 even or is it just neutral? Actually, technically it is even. Anything that's a multiple of 2 would be considered even. Okay, so thanks, Marcus. We got the initial condition down, which we are going to want to use. Okay, so let's go to our 3-step process for solving this. The first step is to basically just ignore the non-homogeneous term on the right side. And so we're just looking at Vn equals 6 times Vn minus 1. And this is, again, a linear recurrence relation. I can do my usual q to the n to solve this. And this one's going to be super easy. Q to the n would therefore equal 6 times q to the n minus 1. And by the time I cancel as many q's as possible, q is just equal to 6. Okay. Right. So that's it. And so my v sub n homogeneous, remember I kind of like to split out the homogeneous term from the particular term. The homogeneous term is just going to be 6 to the n. Actually, there'll be a constant in front of that. There's only one constant here, which is 6 to the n. One thing to remember in this kind of a problem, guys, is that you're not going to solve for the C1 yet. I know you have this initial value here and you kind of want to put in 1 for n and just set it equal to 7 or whatever, but you have to wait until you get the particular solution, which is in the second step of the process. Solving for this constant is literally the last thing you do. So for the time being, we just leave it kind of like this. I might put a box so I can find this in a little while. But we don't solve for that constant yet. Okay, so at this point, we're going to go on to step 2. So far, so good? All right, fantastic. by the way, another quick comment. When we go from here to here algebraically, I canceled as many q's as I could from both sides. Some people might quibble with me and say, well, wait a minute, couldn't q be equal to 0? Because if q is equal to 0, this is certainly true. Certainly looks like it's going to work. But q equals 0 is never going to be a solution in a recurrence relation that you're going to want to have. For one thing, if you added, 0 to the n, you're not really changing anything. So allowing q to be 0 is actually something that we more or less want to just forget about. Because, if you are doing this as a trial solution, and if q is 0, then what are you looking at? You're really looking at v sub n is equal to 0 for all n. That's literally the sequence 0, 0, 0, 0. And that is obviously not the answer to this problem. So generally, you're just going to throw away q equals 0 and just imagine that it would never be equal to 0. Yeah, okay, great. So now let's go on to step 2. This is where we are going to find the particular solution for this v sub n. So I write it as v sub n particular, kind of like this. And you might remember that we only learned how to do this for certain types of non-homogeneous terms. There were only 2 that I covered. One of them is if this non-homogeneous term was a polynomial, and the other one is when it is a exponential. This one is an exponential, and the way that you then transfer over to your particular solution is you create another exponential that's of the same form with some coefficient. I think I used p for this. P times whatever your exponential is. So 8 to the n minus 1. Okay. If this was a polynomial, so just to remind you really quick, guys, if let's say that this had been, I don't know, plus 8n squared or something like that. If this had been what we came up with for the form of our non-homogeneous recurrence relation, then you might remember that for the particular part here, just reminding you here, if this is a quadratic, then what you do down here is you make a quadratic formula in terms of n, and it has to allow for all terms, including a constant term, an n term, and an n squared that goes with this. So you kind of just take whatever the degree of this polynomial is, and you write down a generic polynomial of the same degree. That would mean that you actually, this should be D2. This should be D2. You would have several constants to solve for here in this particular case, right? So just keep that in mind. Depending on the form of what's in the non-homogeneous part of your recurrence relation, that dictates the form of your particular solution. Polynomials of degree n require forms of polynomials of degree n. In this case, degree 2, quadratics, right? But if it's an exponential, then the form of your particular solution is also an exponential. Okay, is everybody with me so far? The only thing left to do here is figure out what p is. It's actually got a specific value. And so what you do is you take this particular form and you just plug it into your general recurrence relation right here. Okay, so I'm going to plug it in on the left side and on the right side. So let's plug this in. Plug this into the recurrence relation. I'll just abbreviate that RR. Plug into the recurrence relation. On the left side, I obviously just have p times 8 to the n minus 1. And then on the right side, I'm going to have 6 times the n minus 1 version of this, which would be p times 8 to the n minus 2, and then plus 8 to the n minus 1. So let's make sure I'm not going too fast. I'm just taking where I have this Vn, I'm just putting p times 8 to the n minus 1, and here's Vn minus 1, which would be p times 8 to the n minus 1 minus 1, which becomes n minus 2. Very good. Some people, by the way, have asked me, when I've done this problem in the past, is it okay if I just do this instead? And just instead of 8 to the n minus 1, can I make the v sub n particular just look like p times 8 to the n? The answer is absolutely that's fine. Because actually, if you think about it, if I just divide by 8 here, 8 to the n divided by 8, is that my phone beeping? Can I get a power surge from you, Jose, after all? Yeah, guys, I'm gonna get some juice on this phone before it dies and I lose all of you. Thank you.
It's long enough. Oh, yeah, there's a little.
Is there a cord I can plug into?
It's right there under the whiteboard.
Okay, I see that, but you know what? I don't think this is gonna go in here.
I do have the other type too.
Yeah, if you have a different one, it might be better because this is the iPhone 14 or whatever. Oh, you know what? I also have a cord, but you have one. Okay, can I just pull this out of here?
Yeah, I have a longer one.
You have an even longer one. Is it for an iPhone? Well, we might need a little bit more length to get this to fit. That does plug into there, so it's okay. But this doesn't have a.
Yeah.
Oh, is that one? He does have that type.
Do you have that thing too? You do. Oh my gosh, you guys are amazing. Okay, let me see. Can I just plug this in here?
I believe that
There might be a little bit of a movement here, guys. I'm just gonna try and move this thing over. Yeah, I tried to charge my phone all afternoon. There we go. That's plugged in there. Now, is this charging? 1 second, guys. I'll be right with you. I just want to see that is not charging. Pardon?
The whiteboard.
Oh, well, that would help. Try that. Come on. Actually, this thing can go straight into there. Why is that not working? I wonder if this thing is not. I saw a spark. But it's not actually working.
Hey, Kevin.
1 second, guys. Quick timeout. I'm going to try and get some more power onto my phone. I have another thing. I just have one of these. That works.
Kevin, too.
That is now charging. Okay, great. We got some more juice on this phone now. There we go. Okay. There you go. Can you guys all see and hear me okay out there?
Yes.
Okay, great. Sorry, we had a little power problem and I didn't want to lose you guys. So I had to plug my phone in here for a second. Okay. Yeah, so I guess the point I was making earlier is I've had people ask me, does it matter if I keep this 8 to the n minus 1 or can I just change it to 8 to the n? It totally won't make a difference. Because if you divide through by 8, which is essentially what you're doing if you replace 8 to the n minus 1 with 8 to the n, this is just a different constant. And so you're just playing the same game. At this point, you could just call this, P1 or something. And so it's still of the same form. Anyway, let's just leave it the way we had it because there was nothing wrong with what we had. And when we plug it in on both sides, is everybody with me? This is what we would have. Let's cancel as many factors of 8 as possible. So on the left side, I'm going to cancel n minus 2 powers of 8 from every single term. So on the left, I'll have 1 leftover power of p. And on the right, I'll have 6p, and then plus 1 power of 8 at the end. Okay? And now if I subtract 6p from 8p, I get 2p equals 8. And so my coefficient p is equal to 4, actually.
If you're to dividing by 8 over n minus 1, why do we have 8 on the left?
So I divided by 8 to the n minus 2 actually.
Minus, okay.
Yeah, so I have one extra p here and
Eight.
Oh yeah, the highest
one
power.
extra,
You
sorry,
divide
one
by-
extra 8 here and one extra 8 here, thank you.
So you
Yeah.
divide by the highest order, right?
The smallest power of 8
Smallest.
is what I actually divided through by, which is 8 to the n minus 2. Exactly. Okay, so my particular term, guys, becomes 4 times 8 to the n minus 1. So it's gonna look like that. So now, step 3 of the process. Step 3 of the process is where we simply add together these two parts. So for step 3, v sub n is equal to c1 times 6 to the n plus 4 times 8 to the n minus 1. All right. And now we're finally in the position where we can use our initial value. So 7 is equal to v1. I'm putting in 1 for n everywhere, and I get 6c1 plus 4. If I did that right. Putting in a 1 for n everywhere. So 7 minus 4 is 3 equals 6c1. And so c1 is actually equal to 1/2 by the time I'm done with that. And so that's the last piece of information that I need in order to write down the final answer. The final answer, then we should write it down. V sub n should be 1/2 times 6 to the n plus 4 times 8 to the n minus 1. Yeah. So that's what we end up with. And again, it wouldn't be a bad idea to just, if you plugged in 2 for n, just see what kind of an answer you're supposed to have. The number of valid keywords or code words of length 2. According to this formula, it should be 1/2 of 36, which is 18, plus 4 times 8 is 32. So it should be 50 of them. There should be 50 valid code words of length 2. Well, I think I can come up with that. You either use 2 7s, or you use a non-7 and a non-7, and there'd be 49 of those. 1 plus 49, yeah, that's 50. So that's pretty good confirmation that you probably have the constants correct. Seem reasonable? Okay, great. Let's keep rolling. Got several more to do here. So that's giving you a pretty good idea. We've done 2 examples. This could easily be a couple real good questions on the exam. Probably quite a bit of points to set up these recurrence relations and solve them. So that's a big deal. Let's go to something else. Talk about a different type of topic here. Let me go to problem 3. This one says, how many ways are there to select n flags? And these flags are all colors yellow. I'll just use Y for yellow, red, or green. So yellow flags, red flags, and green flags. I'll just use Y, R, and G for that to abbreviate it. If the number of red flags must be a multiple of 4. Okay, so the number of red flags must be a multiple of 4. The number of yellow flags must be 0 or 2. And we can have at most 1 green flag. So how many ways are there to do that? how many ways can we take n flags? If the number of red flags has to be a multiple of 4, the number of yellow flags has to be 0 or 2, and the number of green flags has to be 0 or 1. So clearly this is not about graph theory. So we're still dealing with the chapter 7 stuff in terms of counting something. So what do you guys think in terms of the technique or the topic here?
Generating functions.
Yeah, this actually has to do with the generating functions, right? It's not necessarily a recurrence relation, although you might think about that. And I say, well, could it be a recurrence relation? You know, the number of ways to select n flags based off of selecting a smaller number of flags, that might be a consideration. But you could do that, but I actually think so. Like you could say, well, how many ways? Let's say a sub n. We'll just call it a sub n. You might say, well, let's figure out the number of ways to select a suitable number of n minus 4 flags that are red, yellow, or green, and then you could say, well, from this collection, I could then add 4 red flags, because if the number of red flags is already a multiple of 4 here, and I add 4 more red flags, it's still a multiple of 4. Or instead of adding 4 red flags, I could add 2. I could add. Well, that's actually all you could do, because you can't just add 2 yellow flags to this many flags and end up with this many flags. You have to add a total of 4 more flags. So it'd have to be that. I guess the other possibility is you could have had n minus 2 flags that are correct. But it would depend on whether you had already used 2 yellow flags or not. If you hadn't, then you could choose to use 2 yellow flags. Otherwise, this wouldn't have worked. Okay. It's getting kind of complicated. Yeah, so I actually am trying to struggle with this to point out you're not supposed to do it that way. Yeah, this one is going to be done much better with generating functions. So what we're going to try and do, guys, is we're going to try to write down a function g of x. Now remember what g of x is. If it's a generating function, its coefficients are these values of a0, a1, a2, and so on. This is really, we're looking for a function that would give us the a sub n's as the coefficients. Okay? And however, it's maybe not going to be presented that way to begin with. It's maybe going to need to be figured out in some kind of a factored form first, right? So if I want to make sure that I have a multiple of 4 red flags, right? Can somebody tell me what would be a factor of this generating function that would keep track of how many red flags I've created? Which could be 0, it could be 4, it could be 8, it could be 12.
1 plus x to the 4 plus x to the 8.
Exactly. And so on, right? And this goes ... because there's no limit to how many red flags we could have. So these would be the red flags would be determined by choosing a power of x here, right? So I would choose a power of x, and the exponent is how many red flags we're taking. Alternatively, we could do the yellow flags. Not really alternatively, I shouldn't say it alternatively, I should say in addition, we can choose the yellow flags. What would be the part of the generating function that would coincide with the yellow flags?
1
1
plus
plus
x squared.
Nice, 1 plus x squared. I either pick no yellow flags or I pick 2 of them. There's no ... on that. Okay, and then what about for the green flags?
1 plus x.
Exactly. Yeah, just 1, which means you didn't take any green flags, or x, which means you took exactly 1 green flag. Okay, so those are the red flags, the yellow flags, and the green flags represented using a generating function. Okay, and me just erase this here.
Oh, wait, there's more.
Well, this is not the answer to the question. The whole idea here is we're using generating functions to answer the question. So we've set up this generating function. Is everybody comfortable with this? That if I ask you how many ways are there to pick 20 flags? So if n was 20, would you agree that the coefficient of x to the 20th would tell you how many ways there are to do that? You could pick you'd have one term that would just be x to the 20th here, which means you took 20 red flags, no yellow flags, and no green flags, right? Or maybe there's some other way to get x to the 20th to come out. Actually there isn't. But so there would, if you foiled this out, guys, the coefficient of x to the 20th would be 1. Meaning there's only one way, so a sub 20 would equal 1. There's only one way to pick 20 flags if you can only have at most one green flag, you can only have 0 or 2 yellow flags, and the number of red flags has to be a multiple of 4. You actually must pick 20 red flags. You can't pick less than that and combine it with yellows and greens. That doesn't work. Okay. Anyway, everybody out there okay? I've lost some people in Zoom, I think.
Yeah, I'm good.
Okay, we still got everybody here. Okay, good. What you're gonna wanna do is simplify this. So, does this look like anything familiar that we can work with?
Yeah,
What kind of a series is this?
geometric.
Exactly, we have a geometric series here, guys, with the ratio being x to the 4th. So that first factor is like 1 over 1 minus x to the 4th, right? You can just view it in those terms. If you rewrite this out, it would be 1 plus x to the 4th plus x to the 8th plus x to the 12th and so on. So we have that, and then we also have 1 plus x squared, and we also have 1 plus x. Okay? Now, can this be simplified? Absolutely. The denominator here is actually a difference of squares. So I can write it as, so I'm going to leave the numerator the same, first of all. But the denominator can be factored as 1 plus x squared times 1 minus x squared. And that actually cancels. And not only that, the 1 minus x squared also factors as a difference of squares. So we can write it as 1 plus x times 1 minus x and do more canceling. We actually just get 1 over 1 minus x. Which, if we now go back and write it as a series again, is actually 1 plus x squared plus x cubed and so on. And that is telling me the answer to my problem. Because the coefficients of these powers of x, those are the a sub n's. So a sub 0 is 1, a sub 1 is 1, a sub 2 is 1, a sub 3 is 1. Actually, guys, a sub n is equal to 1 for all n. Does that seem right, conceptually? If I ask you to grab 17 flags, is there really only one way to do it? Well, it better be. If I ask you to grab an odd number of flags, then that means you must take the green one. Right? So you must take the green one, and then the number of reds and yellows will depend on exactly how many are left. Well, if I've grabbed one green flag, then I have 16 more flags to grab. Just like with 20 flags, 16 is the same deal. You must pick 16 red flags. You can't take any yellow flags. You can't take 2 yellow flags, because if you did that, you'd have to have 14 red flags. 14 is not a multiple of 4. 14 is not a multiple of 4. So yeah, you actually are very much restricted in how many ways there are to do this. It all depends on whether this is even or odd, and then whether if it's odd, if you subtract 1 from it to get an even number, the resulting even number then it's a matter of whether it's a multiple of 4 or whether it's too off from a multiple of 4. So if this was 18, if there were 18 flags, now in this scenario, you must pick 2 yellow flags and then the rest of them all red, and you can't take the green flag in that case. So yeah, there's actually only one way to do it for every value of n. That makes some sense? Yeah, was it?
Would you want us to focus on like the derivative, antiderivative part of this?
In this problem, we don't need to do that, but I was just about to say that we've learned that in general, if you take derivatives of this, so like the derivative of 1 over 1 minus x is 1 over 1 minus x quantity squared. The expansion of that, of course, is really just, we know what the terms are here. For this particular geometric series, or sorry, for this particular generating function, this will be giving us a sub n equals n plus 1 as the coefficients. You can see that. A0 is 1, A1 is 2, A2 is 3, A3 is 4, and so on. In general, so this is just to review, this is something to look back over in your notes one more time if you need to. But in general, if we take 1 over 1 minus x and we raise it to the kth power, this one turned into a series n going from 0 to infinity of n plus k minus 1, choose k minus 1 times x to the n. Do you remember the stars and bars coefficients showing up here? Yeah, so the one right here is just when k is equal to 2. If k is equal to 2 here, you just get n plus 1 choose 1, which is n plus 1 for the coefficient. If k is equal to 1, it's just this one. And that's just n choose 0, which is 1. But this can be generalized for any value of k. So this one's worth memorizing, and this is sort of derived by taking the derivatives of the original basic one right here. This is the most important one. This is the one that everybody has to know at graduation. Off the top of your head, have that one memorized. But then, yeah, you can take derivatives, or we could take integrals of these two. I think we've done the trick with integration a couple of times. The issue with integrals, of course, is you do get some fractions showing up. So sometimes fractions don't make sense as representing a real world problem. So if the coefficients turn into fractions, it's sort of like, well, what kind of a problem would represent that? And that's maybe harder to come up with. I don't think we've done any examples like that. But yeah, you can take these series and do derivatives and integrals and create other generating functions really quickly from that. Yeah, Marcus.
Sorry, so what was the use of the derivatives in this problem? Or in problems in general?
Just if I wanted to, like, just as an observation that the generating function for the stars and bars coefficients is basically this function. So this is a closed form. Remember, a closed form just means there's no dots. It's not like an infinite summation. So if I ask you, what's the generating function for the stars and bars formula for some fixed value of k? You could say this is the answer. But actually, this is not a closed form answer. This is. So if I asked you for a closed form answer, this would be the answer that you would be able to get. Yeah. Let me do another example to kind of hit that point home a little bit more. Yeah, go ahead.
But also, different question.
Yeah.
But if the closed form is like kind of ugly, how might we answer this? Because it doesn't ask us for a generating function or a closed
It doesn't.
form.
No, it
It
doesn't.
wants the a sub n sort of answer.
Correct.
How
Right.
would you answer that, you think?
So in this case, we have two choices. We can either do exactly the way I solved it here, which is to use the generating functions, or we can try to avoid using the generating functions and just do the reasoning I just gave you, which is that, well, depending on whether n is even or odd, that just dictates whether I have to use the green flag or not. It's kind of a problem by problem
I see.
analysis. It's not like there's like a one
Right.
procedure answer for that.
We hope that you show mercy.
We hope that something's doable.
Yeah.
It's gotta be something very reasonable.
Take on.
Yeah, let me give you another problem, that I think might help you see a little better about this. We did not spend a lot of time on generating functions. I think there was one homework on it. So I would not expect the exam to have more than one question on this topic, if at all. But if I did, here's another example that I could give you. I could say something like this: what is the coefficient of x to the 12th in the quantity x cubed divided by 1 plus 4x quantity squared? So here's where Marcus is going to ask me, why would you ever want to know that, right? Who cares what the coefficient is? Well, if this is the generating, this is my g of x, right? If this is the generating function for some sequence of values that represents something that you're counting, then a sub 12 is this coefficient, and I want to know what a sub 12 is. Maybe this is the number of ways to select my flags given certain conditions. And if that was the case, then what if I ask you how many ways are there to choose 12 flags? Well, it's this coefficient. So we have to be able to find these coefficients even when it's expressed in a closed form. You might think, well, wouldn't I prefer the ... form? In this case, I would, because I'd love to have ... dots and just go out to x to the 12th and read off what the coefficient is. But I might have derived this by using derivatives or integrals or multiplying through by something. So I need to be able to take something like this and extract a coefficient out of it. Yeah, so the way I would probably pursue this one is I would first say this x cubed is already giving me 3 powers of x out of the 12 that I need. So I'm really going to focus on getting 9 more powers of x out of this denominator piece, right? So equivalently, we want the coefficient of x to the 9th in 1 over the quantity 1 plus 4x quantity squared. So if I get the coefficient of x to the 9th out of that, then by the time I power it up with an x cubed on top, it'll be the coefficient of x to the 12th of what I originally started with. Does that make sense so far? Okay. This should look like I took the derivative of, because over here, right, when I take the derivative of 1 over 1 minus x, I get 1 over that same thing squared. So I am tempted, just maybe I'll call this scratch work because maybe I don't quite see how this works yet. But if I took 1 over 1 plus 4x, by the way, I'm pretty sure that I could write a power series for that. I could write this out as a series. But before I do that, let's just take the derivative of this and see if it's anywhere close to what we want to take the derivative, what we want as a series to look at. So this thing, by the quotient rule, I have to take the denominator squared on the bottom, and then I do low d high minus high d low. The d low is 4, so it should be -4 there actually. Okay, so everybody with me? So we want the coefficient of x to the 9th in this guy. But if I can figure out the coefficient of x to the 9th in this guy, it's almost the same. It'll be off by a factor of -4. So I want the coefficient of x to the 9th here, and then I'll just tweak it to get the coefficient I really want. And to get the coefficient of x to the 9th out of here, I am simply going to figure out the coefficient of x to the 9th on this thing. Okay, so let's come over here. this is the cool use of derivatives and integrals. Somebody was asking me, why do we sometimes use derivatives and integrals on these? Well, see, 1/1 plus x to the 4th prime. I can write a power series for this. Because this is basically like, let me write it out in total detail. This is like 1 minus negative 4x, right?
Mhm.
And now I've got like 1/1 minus blob. Well, my series for that is 1 plus the blob squared plus the blob cubed, and so on and so on. And in fact, and then sorry, there's a prime on that. There's a prime on that. So I'm gonna have to take a derivative here as well. So I'm putting primes on everything here, guys, derivatives of everything. And let's just see what we get for these derivatives. When I take the derivative now term by term, the derivative of 1 is 0. The derivative of negative 4x is negative 4. The derivative of negative 4x quantity squared, that's going to be 2 times negative 4x, right? Basically, you're taking x squared. The derivative of that is 2x, and there's a negative 4 in front of that. What about the next term? The next term is 3 times negative 4x squared. Actually, no, I am not doing this right. Let's try this again. Sorry. The derivative of negative 4x is negative 4. This is just negative 4 squared times 2x. Let's just do it that way. And then this one is negative 4 cubed times 3x squared. So I'm splitting this apart as negative 4 squared times x squared. Negative 4 cubed times x cubed. Right? And then the next term would be negative 4 to the 4th times 4x cubed. And I go on and on and on. And which coefficient am I looking at? It's x to the 9th that I want. So I'm going to keep going here, gang. Give myself some more room. With me? So I keep going, and eventually I'll get what? If I want to get the x to the 9th coefficient, which term will that be? What power of negative 4 do you think I'm going to have?
10.
The 10th power of it, right? And then times what?
10x to the 9.
10x to the 9th. That's exactly right. So the coefficient of x to the 9th is that guy. Now, that's the coefficient of x to the 9th for this thing. Right? But actually for this thing. But then the question is, what is the coefficient of x to the 9th for the original thing we wanted the coefficient of x to the 9th of?
Negative 4.
I take that, and what do I do to it?
Divide negative 4.
Divide by negative 4. Right, because this one already has an artificial negative 4 on top that I didn't really want. So to get back to this coefficient of x to the 9th, I have to take this coefficient of x to the 9th. Every coefficient here has been inflated by a factor of negative 4 because you've thrown that factor through every term. So this is the coefficient of x to the 9th for my scratch line. But then to go back, to get the answer to our original question, we would need to take negative 4 to the 10th times 10 and divide it by negative 4. And so the correct answer is negative 4 to the 9th times 10. As it turns out, this probably isn't a real good physical problem because that's a negative number. So we're not really counting something. It's like not a negative number of ways to do something. But it still gives you kind of the idea of how generating functions could be used to solve for a particular coefficient. Yeah. Okay. Sweet. Everybody so far so good? All right, great. I am going to, problem number 5 is a Fibonacci example. I'm gonna skip that one for now and go on to some of the graph theory. And then I'll come back. Like I said, I can tell already I'm not gonna get through all these problems by the end of tonight. So I'll come back on Wednesday and I'll start with the ones that I'm not getting to do tonight. But there's only 10 total, and I think actually the graph theory ones are easier overall, I think. It's just my rough feeling about it. So I'm gonna skip number 5, guys, and I'm gonna go straight into number 6. Okay. And then here is what this says. If G is a connected planar graph with at least 5 regions. So remember, for a planar graph, you can talk about the regions that it creates when you provide a planar representation of it. Question is, what is the minimum number of vertices possible? What is the minimum number of vertices that you could have in such a graph? You have to have at least 5 regions. So the question would be, how could you do that with as few vertices as possible? Now each region, if you remember from my video, the regions, basically are created at least, out of a triangle, if not more. So this would be a degree 3 region. This is a region here of degree 4. The degree is just a number of boundary curves, the edges that you have on the region. So here I've managed to create one region using only 3 vertices. Here I managed to create one region, but I used 4 vertices. Question is, if I'm trying to create 5 regions and I want to use as few vertices as possible, what would you have better luck with? Using the triangles or using the squares? Yeah, use as few vertices as you can. You're trying to use as few vertices as possible. So maybe we could even just try and make it out of a bunch of triangles. So here I've already got one region and I used 3 vertices. By just adding one more vertex, I could make another region like that. Right? I'm trying to create, and actually at this point I already have 3 regions, because don't forget the outside is also considered a region. So maybe I can make, how can I make another? I could just draw another triangle out here if I was kind of doing the same thing I did before, but is there something else I could do that would be even better? Another diagonal.
No,
So I'm gonna make a planar representation, so I don't want to cut through the middle of it.
What if you can use kind of like make a semi-triangle using the 2 versus outside?
So go around like that.
Yeah.
Okay, so here I didn't even add any new vertices. And now I have 1, 2, 3, 4 regions. So that's great. We didn't even have to do anything for that. Now, would I be able to maybe do this as well? Careful. Actually, this picture is not a graph anymore, because I have 2 edges going between. So this would be what this would be considered a multi-graph, because you actually, it doesn't look like it, but you actually have created 2 edges between the same 2 vertices. So guys, when I say something is a graph, that means it's a simple graph. So it does not have loops. It does not have multiple edges. So I would not be able to do that one. Okay, but we're really close to getting what we want. I think we should be pretty close. What about just putting another one in the middle? So that adds another vertex, but then I can like do this, can't I? And now I have tons of regions. That's actually maybe even more than I needed.
Get rid of one of the edges.
Pardon?
You can get rid of one of the edges.
You could even get rid of one of the edges, although it doesn't really ask you to minimize the edges. It's just minimizing the vertices. So we can do it with 5, right? I mean, you can see here, I've got even 6 regions, and I've got only 5 vertices. So the answer to this is we definitely can do it with 5 vertices. Could you do it with 4? So we could draw 4 vertices here and try our best to see if there's a way to make 5 regions out of this. So I can obviously start with a triangle like that. And then I can try to, do something else. I can make this like that. I can go around like that. That's 4 regions. Can I add one more region somehow without using? I mean, see, the problem here, guys, is actually what you have a picture of is K4. Which means if you don't add another vertex and you try to make another edge, you are for sure going to be duplicating an edge. Because if I've already drawn the graph of K4, then every edge is already there. You can't add any more edges with those same vertices without creating a double edge. So I actually claim that this is not going to be possible to make a 5th region here. Because I really can't change this picture in any fundamental way. So I believe the answer here is n equals 5. And here's the picture for it. Actually, we can get 6. If we're willing to go up to 5 vertices, we can actually make 6 regions. It's even better than 5.
When we're proving this, is that good enough? Like I found this.
No, it's not. So I would like to prove, because you might say, is this a proof? Obviously, drawing the picture is great. That shows me that the minimum number is at least 5. But you have to convince me that you couldn't do it with 4. So you could talk about the fact that K4 can only give you 4 regions, and that's the most number of edges you'd be allowed to draw. But there's actually a nicer way to prove this. There's a nicer way to prove this using information about connected planar graphs. Does anybody remember any equations involving regions and vertices for this kind of graph?
Euler's formula?
Yeah, we could use the Euler's formula, right? So maybe let's see if we can give a proof here. Euler's formula, this is the one that says, r minus e plus n is equal to 2. So for a connected graph, it would be equal to 2. And we're saying that r is going to be at least 5. So this one, I'm going to use a greater than or equal to here, is at least 5 minus e plus n. So the r is greater than or equal to 5. So we would have that. So if I just kind of turn this around, so what is this saying? 5 minus e plus n is less than or equal to 2. We could just do it like that. And maybe we can rearrange this one. Subtract the 5 from the 2, we get 3 is less than or equal to e minus n. Do we know anything else besides the Euler's formula? If we have a connected planar, by the way, if you have at least 5 regions, you definitely have several edges. You can't do that with only one edge. Yeah.
Oh, that's E is less than or equal to 3 and minus 6.
All right. So this was the other one. If you guys watched my videos, right, you know that in a connected planar graph, as long as there's more than one edge, which there clearly will be, you can't draw 5 regions if you only have one edge. So this is also true. So maybe I can feed this in there as well. So the E here is less than or equal to 3n minus 6, and then we have that with a minus n on it. Okay. So putting this together, here's 3 less than or equal. Let me use the transitive property of. So the 3 on the far left is gonna be less than or equal to whatever this is over here, and this thing can be written as 2n minus 6. Because I got 3n minus n, 2n minus 6. If I add the 6 back to the other side, 9 is less than or equal to 2n. And now, if you solve for n is greater than or equal to 4.5. Well, it can't be equal to 4.5. It has to be a whole value. And the smallest whole value that n could be would be 5. So there's your proof. So because it has to be an integer, n is at least 5. Yeah, that's how that's going to work. That makes sense? So when you see that you're working with a connected planar graph, and they're talking about numbers of regions and number of vertices, and even if this one doesn't specifically mention the number of edges, but anything involving the regions, edges, or vertices in a connected planar graph, you want to be thinking about this and this. And even if you don't quite see how to do the proof, if you write this down, I'll give you partial credit. If you write this down, I can give you partial credit. If you draw me the picture, I can give you partial credit. By the time you've done all of that, you might not have totally gotten the proof perfect, but you will get a good chunk of the credit for that problem by having all the key tools there. It's just a matter of putting the tools together in the correct way. Actually, what I would probably do is I would write all that stuff down that I knew quickly. And then if I was kind of stuck on this, I would just let it go. If this was on the test and I didn't quite see how to like put all these inequalities together, I would just write down the facts that I do know. That should take 30 seconds. And then I would go on to something else on the exam and come back to this one a little bit later after you've had time to get the rest of the exam done. Guys, do not get bogged down on one problem. Okay, try to keep moving, get your momentum going, and I know it's frustrating. I was a student not that long ago. I always hated like leaving something that I didn't have it quite done. But in terms of like your overall exam score and everything, you will do much better if you keep moving forward as best as you can. So write down what you can do that doesn't take a huge amount of effort. And then if you're getting fumbled up in the algebra here, I'd let that go, at least temporarily. And then, yeah, maybe I'll give you a chance to take something home. But even if I don't, you'd have gotten a lot of partial credit from just writing down what you did know. So it's definitely worth doing. Okay, are we good here? Okay, sweet. Let's do number 7. So this one's asking for an example. So this says, draw an example. Draw an example of a connected graph of order 7 that contains no Eulerian trails, no Hamilton cycle, and we're actually going to do a 2-part problem here, guys. The first part, part A, is going to be non-planar. And then part B is going to be to do another one where it is planar. So we'll do a non-planar one, and then we'll do a planar one. We'll start with a non-planar one first. Okay, so we want to have 7 vertices in total. We don't want there to be any Hamilton cycles, no Eulerian trails. That's open or closed. It doesn't say which kind it is. So remember that for Eulerian trails to exist, you mostly have to have even degree vertices. If they're all even, you can actually make a closed Eulerian trail. If there's exactly 2 odd vertices, then you could have an open Eulerian trail. By the way, you can't have one odd degree vertex. By the handshaking theorem, right? The handshaking theorem says if you add up the degrees of all the vertices, you have to get an even number. So if there was one odd degree vertex, then you'd have an odd number with a bunch of even numbers added to it. That would never become even. So the number of odd degree vertices is either 0, or it's 2, or it's more than 2. And that's the only possibility. So if I want to have no Eulerian trail, I'm going to want to make a graph that has a lot of odd degree vertices. And I have 7, let me just draw 7 vertices around here. Right, and I want the graph to be non-planar. Does anybody know any graphs that just kind of off the top of their head, you know that they're not planar? K5 or K33, exactly. Now, neither one of those has 7 vertices, or that would be great.
Well, we can make a subgraph.
But we could have a subgraph that's, we could take 5 of these 7 vertices, for example, and draw a K5 out of them. Let's just do that. Let's ignore the 2 on the bottom and let's make a K5 out of these vertices that are here, guys. So if I do this, I'm not done with my picture yet, but I've got to start on it. This has K5 in it. And so I already know that this is non-planar for sure, because if you have K5 as a subgraph, I'm really talking about Kuratowski's theorem, which I'm going to go into a little bit more tomorrow. Kuratowski's theorem just says that any non-planar graph basically either has K5 inside of it as a subgraph or K33. Right? So if I have this as part of my graph, I'm for sure going to have a non-planar graph. Or I could have tried to do it with the K33. But let's start with this. Now, as it stands right now, the vertices have degree 4, 4, 4, 4, and 4. Everything is even. We remember what we said a minute ago. We want to have a lot of odd degree vertices. So is there a way to now change this so that I do have 3 or more odd degree vertices?
Make K6.
So we could make K6,
Like connecting
which would
one
add
point.
this vertex to all of the others. So let me tell you that you might wonder, well, why don't you just make K7? You could, that would definitely be non-planar because K5 is part of K7. The problem with the complete graphs is they all have Hamilton cycles, right? So you might say, well, I could do K6 and then deal with this last vertex. Maybe I could create a bridge or something like that. Well, maybe that does work actually. I haven't completely thought about that. So I could make a K6. Let me just try that. We're gonna play with that idea. I'm gonna go ahead and add all of those edges there. At this point, now almost all of these vertices have odd degree. And the problem with this picture is, so there's no Eulerian trails. It is connected. It has order 7. It's not planar, but the issue is the Hamilton cycle. So what you would need to do is like do something like that. Because you can't go visit this vertex and then leave again. Because it's supposed to be a cycle. So if you went and visited this vertex, the only way to do that would be to visit this vertex twice, which you're not allowed to do. So does this work? So that's degree 1, that's degree 6, and the rest of these should be 5, right? Yeah, so that's too many odd degree vertices. There's no Eulerian trail. There's no Hamilton cycle. It is connected. It's not planar. It has order 7. I think that's good. I think that does work. The way I did it, to be honest with you, I did it a little differently in my solution. I just took K5, the original K5, and I just added one extra edge like this. It's kind of the same idea, right? And this will also work. You'll have 4 vertices of odd degree, and again, you can't have a cycle. Guys, if you have vertices of degree 1, there's no way to have a Hamilton cycle with that. So these are called pendant vertices when they have degree 1. And if you have any vertices of degree 1, you would never be able to do it. Okay, so that's a non-planar one. Everybody good on that?
Actually, sorry, never mind. Yeah, you have 4 odd vertices.
Yeah. Okay, great. So that's the first part. Let's try and do part B. Can we make something that is planar, but again has no Eulerian trails, no Hamilton cycles, it's still connected and so on.
Okay, 1, 2, 3. Yeah, can we just get rid of pretty much just make like a circle with the one?
All right, so this is for part B.
Yeah,
Let me just take my 7 dots around the outside again.
yeah, like the same thing, but instead it's just like we have 2. Everyone has 2, except for the last one that's gonna have 3.
So you're gonna go all the way around.
Yeah.
Oh, like this you mean? And
Yeah,
then connect that?
Yeah.
Let's check that. That's obviously planar. It's obviously connected. It has order 7. It has vertices. There is an Eulerian trail here because we have 2 odd degree vertices. So can we change it?
Just take off an edge in the middle.
Take off like
Right.
that?
No, like
Oh,
another one, like maybe to the left of that.
go to there?
That's also open. You could like
No, that doesn't work.
restore the edge that you had before, and then take off the edge to the left of the one that you removed.
This one?
Yeah.
Let's check it. So now we have a 1 and a 1. 1, 3, 2, 2, 2. Yeah, we actually drew a tree at this point, by the way. This is a tree. There's no cycle. I should have added that to the question too. There's no Hamilton cycle. There's too many odd degree vertices. It obviously is planar, has order 7. Yeah, that would totally work. There'd be lots of right answers to something like that, but yeah, creating examples for some of these is, definitely a nice thing to be able to do as well. So yeah, I kind of like that one. Okay, let's see what else I want to do. I have one where let's do one more tonight. Is that okay? It's already 7. Can I go with one more?
Mhm.
Okay, let's do one more, guys, on tonight's review, and then I will actually have done almost basically 3/4 of this set. I'll only have to do a few more on Wednesday, and then I'll be ending up cycling back to the first ones again. But I'll do one more, and then I'm going to take a break to go grab something to eat, and I'll come back later tonight as well at like 8:30 or so. So let's skip number 8 for now. I'll do that one on Wednesday. Let's go to number 9. I put a problem like number 9 on your quiz, but the one that was on the quiz was like probably too easy. Everybody got it right pretty much. It's where graph isomorphisms preserve properties. So the one that was on the quiz was preserving 5 cycles. If there was a 5 cycle in one graph, and if that graph was isomorphic to another graph, then that other graph was also going to have a 5 cycle. That's pretty easy. Here's one that's a little bit harder. So let's prove, and you should expect I'm probably going to ask you to prove something that's got a little bit of meat to it. So if we have an isomorphism theta from G1 to G2, so if this is a graph isomorphism and G1 has a Hamilton cycle, then G2 has a Hamilton cycle. So this is an interesting one to try to write down. So if there's a graph, if the first graph has a Hamilton cycle and it's isomorphic to another graph, the second graph has a Hamilton cycle. By the way, probably before I ask you to prove this, there'll be a part A, which will say, define what a Hamilton cycle is. So be sure to review your definitions, guys. So make sure you know what a bipartite graph is. Make sure you know what a Hamilton cycle is, Eulerian trails, all that kind of stuff. Be sure you can write those things down. So what I would probably do here is I get a little bit of notation going. So my first graph G1 consists of a vertex set V1 and an edge set E1. And then the second graph would have a vertex set V2 and an edge set E2. So you would like start with something like that. And we could exhibit the Hamilton cycle in G1. So let's let the first vertex set be, I don't know, little v1, little v2, dot, 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 up to little vk, and assume we have Hamilton cycle. And you can write your cycle this way, guys. V1 with an arrow to V2, with an arrow to V3, and dot, 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 with an arrow to VK, and then with an arrow back to V1 again. Without loss of generality, you can assume that you listed the vertices in the same order that they're going to show up in the cycle. One thing that people have been forgetting to do, I've seen several people doing this, when you have a cycle, you should draw the last edge that goes back to the starting point. Some people have been stopping their cycles like that, and they're okay. I forget. There was actually several people on the last homework that did that. So you're going to want to include that edge just for thoroughness right there. Okay, great. So we have this Hamilton cycle this is in G1, right? So that's in the first graph. So in G1, we would have that. What we want to do is construct a Hamilton cycle in G2. Okay, so do we have a proposal for what that cycle would be? Go ahead.
I would say something like we have distinct vertices in G1.
Yeah, these are kind of distinct.
Then we have, we know there's a graph isomorphism.
Correct.
And we have theta of the vertices,
Of each of them, yeah,
right?
exactly. So we have like theta of V1. And then do we know anything about whether there's an edge from there?
Yes. There's a graph isomorphisms preserved.
Let's just add that here. By the way, writing something like that down, even if you're like a little shaky on the rest of the proof, if you just write down, since graph isomorphisms preserve edges, this will get my smiley face out, right? Just seeing people write that down, that's what an isomorphism does. So we have this edge, for example, right? So I know that there's an edge from theta of V1 to theta of V2. Okay, and then what else am I going to write down?
Going to theta V3.
Exactly, and then we can just go like the same format that we have down here, all the way to theta of VK, and then again, we should make sure to finish it up by going back to theta to V1. All of that is guaranteed because edges are preserved. Now, if you only wrote this down and that was all that was there, I might have a slight beef with you about it. I might take off a point. It wouldn't be too bad. I might, you know what I mean? I might like have a slight little get my red pen out thing because I have to know that all of the vertices of G2 have been visited. Because that's what, like, how do I know this is, I can see it's a cycle. It starts and ends at the same point. But I have to know that every vertex of G2 has been visited. Could somebody explain why I know that?
Oh, because we would have the same amount of vertices.
Yes. Awesome. Note that G2 also has K vertices. So V1, we set up V1 to have K vertices. So the second graph also has the same number of vertices because the graphs are isomorphic. So since G1 is isomorphic to G2, if you want to add that, you could do that. So it has the same, it also has k vertices, and so actually. I see k vertices here. And also I know that these are all distinct from each other. We have not taken one cycle and then somehow created like a figure eight or something like that. This actually has to be distinct vertices because theta is injective and surjective. It's one-to-one and onto. So distinct vertices get mapped to distinct vertices. So all of these are now distinct as well. So I'll just say since theta is one-to-one and onto, we have k distinct vertices, which are theta of v1, comma, theta of v2, comma, dot, 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 up to theta of vk. And so every vertex, and so thus, we have a Hamilton cycle. Every vertex has been listed in that cycle that we wrote. Yeah. Does that make sense? So this one's a little more work than just saying, oh, there's a 5 cycle in this graph, therefore there's a 5 cycle in that graph. And it's just because the definition of Hamilton cycle is a little trickier. If you want one that's even slightly harder than this, I'm gonna save it until. Actually, it's not on this review sheet. It would be a good one, which would be, if you want one to practice that is not in any of the review materials as far as I know, unless it was something I did before, an even harder one would be bipartite. If G1 is bipartite and it's isomorphic to G2, then G2 is bipartite. This is a messy thing. This is, oh, we gotta do the 2 camps.
Need 3 things.
Right, all the definition is just kind of messy because you gotta have 2 camps of vertices in the first graph. And then you gotta have 2 camps in the second graph, and you have to prove that, the edges only go from one camp to the other. And if that's true in the first graph, then it has to also be true in the second graph. So that one, because the definition is even a little bit more cumbersome, the proof becomes even a little bit more writing than this. Yeah, Kevin?
From there, for the bipart, if we have to take care of the bipart, we also have to talk about adjacency of the the vertices, right?
The adjacent, so there's no edges within, for
Yeah.
vertices within the same camp. Right, so yes, you would have to clarify all that. So remember that isomorphisms preserve non-edges as well as edges. So you could use that to help you. Another thing you could do is you could say, I don't like the definition of bipartite very well. So to do this problem, I'm instead going to use my theorem that Dr. Annan proved, and some of you guys used this theorem really nicely in the homework that I just graded, the last homework, which is that a bipartite graph, really, it's just a graph where there are no cycles of odd length. So you could use that. You could say, oh, well, if G1 has no cycles of odd length, then neither will G2. And you could do that by contrapositive. If G2 has a cycle of odd length, then G1 would have had a cycle of odd length, basically the same as the way the quiz problem was worded.
How would we put it in like, we should just say, does it have cycle of odd length? But how would you write it down like this?
You would need to like create like notation for your cycle. Your cycle
Yeah.
could have like vertex V1 to V2 to V3, and maybe the last vertex would be V2n minus 1. Right? And then you would then again sort of just apply theta to that cycle. That's what most people were doing on the quiz problem. And then you get a cycle of exactly the same length.
Oh, okay.
Right? So the oddness or evenness of the cycle would be preserved then.
I was just saying because it's like every cycle has to be even.
Right, so you could say, suppose that's not true for G2. Then there would exist one odd cycle in G2.
Oh, yeah.
And then by taking, actually in that case, you'd be taking the inverse isomorphism back to G1 and say, in G1, there was an odd length cycle.
Cause I know you don't like it, oh, just because it's.
That's okay. I could ask you to prove this from the definition. I might say in part A, what's the definition of a bipartite graph? And then part B might be use that definition to prove this. I might let you try that. By the way, guys, the other thing as we're wrapping up here, you're allowed to use the theorems that we've covered in the class, but you don't need to know the theorem numbers. If you don't remember which theorem number it was that said that a bipartite graph has only even cycles, you can just say that as a theorem from class. You don't have to have the numbers memorized. So just to make your life a little bit easier. But get some flashcards going with all the definitions and theorems. I'd recommend you want to have those at your fingertips, not shaky. You want them super solid. You can pull them out whenever you need it.
Still raining, sorry.
All right, guys. Everybody in Zoom land, I am going to turn this off if we're good for now.
Thank you.
You're welcome. Thanks for coming. And that's a wrap.